So today I want to discuss with you the I call mathematical impedance transformation. In contrast to the Smith diagram, we want to assume now that our transmission line has certain losses, so we will have here gamma L, and you know in the Smith chart you can only do the transformation easy for lines which have no losses, and thus gamma goes over to beta, but today we will discuss gamma to show a complex value. And we know as soon as we terminate the transmission line at the point L with a certain load impedance, there will exist some reflections on the transmission line, and the voltage at a certain point on the transmission line is given by the superposition of the two waves, or the interference of the two waves. So we can write that I have u of z will be the incident wave ue times the exponential function of minus gamma times z plus ur times the exponential function of plus gamma times z. You know that the negative sign denotes a wave which travels into the positive z direction, and the positive sign describes a wave which travels in the opposite direction. Beside the voltage wave, we can also define the current waves which are also a superposition, and we can write it like this: that is the characteristic impedance times the current at a certain point z, and this is of course again a voltage, and you see now it's the incident voltage times the exponential function of minus gamma times z. But here we must remember that the current of the reflected wave travels or flows in the opposite direction, and we will have this is minus ur times the exponential function of plus gamma times z. So these two equations describe the voltage and current distribution along the transmission line for an arbitrary point z along the transmission line. So we can define here, for example, the input voltage u in, which would be, I can write here u in, but this is nothing else but the voltage at z equal to 0. So the exponential function will disappear, and also here, and the input voltage will be given by ue plus ur, just the addition of the two complex amplitudes. And for example, for the input current E in, which is flowing also at the point z equal to 0, we can say this is zc times E in. And of course you see here also the z coordinate will disappear, and we will have this is ue minus ur. And to calculate now the input impedance, we just can divide the two equations, and we will find u in over zc times E in. And of course, if I have the u in divided by E in, this will be nothing else but z in, so we will get the input impedance I see into this transmission line with reference to the characteristic impedance is just given by the ratio of UE plus UR divided by UE minus UR. So this will be the input impedance, but still unknown are the amplitudes of the complex amplitudes of the incident wave and the reflected wave. To get this, we can here define, for example, the voltage UL, the voltage at the load. And of course you see here, if I use this equation, then the voltage at the load can be written as UL, it's equal to the incident voltage times the exponential function of minus gamma times L plus the reflected voltage exponential function of plus gamma times L. So the voltage over the load is given now by these expressions, and of course I can also now set up the same equation for the current EL. So I will define ZC times EL, and this will be then UE times the exponential function of minus gamma times L plus UR, here we will have a minus sign of course, and here we have the exponential function of plus gamma times L. So you see what we have here is we have two equations which give the relation between UE and UR and UL and ZC times IL. So it's easy to solve this equation for the amplitudes UE and UR, and what we can do is we can insert the result of this into this equation, and then we will get an equation for the input impedance as a function of UL over UE, which will be the output impedance, the load impedance, sorry. So, but of course this would be very time consuming, so I will omit this and give you directly the result. If I solve these equations for UE and UR and put it into this equation. So now I will give you the result for the input impedance. Of course the input impedance set in is nothing else but the voltage U in divided by the current U in at this port of the transmission line. And if you go through all the mathematics, you will find that the input impedance set in will be equal to ZC, and here we will have ZL over ZC plus tangents hyperbolicus gamma times L, and we will have here 1 plus ZL over ZC, and here also the same function tangents hyperbolicus gamma times L. Of course this is a quite complicated equation because you have to take the tangents hyperbolicus of a complex value. So this is the equation how a transmission line with losses transforms the the output impedance or the load impedance into an input impedance. So this is for a transmission line with losses. So normally this equation will be implemented in some simulation programs. In a simulation program it's easy to also to account for the losses, but for the further discussion we also need some equations for the case without losses, and then we will have in the lossless case we will have that gamma goes over to J beta, and tangents tangents hyperbolicus of gamma goes over to J tangents. Here we must write gamma L, or gamma L, and here it goes over into beta times L. So we have to replace the tangents hyperbolicus function by J tangents beta L. So in the case without losses we will find that we have the input impedance set in, it's also set C times, and here you have now the load impedance with reference to the characteristic impedance plus J tangents of beta L, and this must be divided by 1 plus set L over set C tangents, or also here a J tangents beta L. So this is the equation we will discuss in the next step. So even so this equation is not so complicated than this compared to this, but we will also only here discuss some special situations. So we will have first right here, this is the formula for the transmission line without losses. So of course, compared to the Smith chart, so in the Smith chart the transformation is quite easy, but if you would do a mathematical transformation it's more complicated. Of course today with all the possibilities of computing it's no more a problem than it was years ago. I want to discuss now special situations of lossless transmission lines, and one very important point here, or one important application, is the so-called short circuit stub. What does this mean? We have a transmission line of a certain length, and this transmission line is described by its characteristic impedance ZC and beta, because we assume a lossless transmission line, and at the end of the transmission line we assume that we have a short circuit here, which results in the point that ZL is equal to 0. The load impedance is equal to 0, and of course the transmission line here still will have a certain length L. Here this will be the length L, and the input impedance will be the impedance I see into this port of the transmission line. And if we change our impedance, our formula for the impedance transformation, we will find that the input impedance in this case is given by J ZC tangents of beta L. Of course, where we will have that beta L will be equal to 2 pi times L over lambda. So this is the situation here, and of course you see that we have a purely imaginary input impedance, so I want to sketch the behavior or the imaginary part, so I will here sketch the imaginary part of set in over the length beta times L. This is the angle in principle, and here we have 0. And we know that the tangent function itself is a periodic function, so it's easy to sketch it. So in the first step we can say here we have the angle, it's pi over 2. Then we will have here the angle pi. And then we will have here the angle 3/2 of pi. So, and we know that the tangent function itself goes to infinity as soon as the angle approaches pi over 2. And of course, also here we will have a pole in the tangent function, and we know that the tangent function is a periodic function, so it looks almost like this. It starts at 0 and then goes to infinity, then it will change to minus infinity and undergoes a 0 and then goes to infinity again. So this is because the tangent function is periodic, and of course we don't assume that we have some losses here. So here we have the purely our tangent function. And now we can think which lumped elements we can realize with a so-called short circuit stub. And you see its imaginary part is first positive, so I can also write it like this somehow. This is 2 pi L, and lambda is nothing else but C times F. So this is also in principle the frequency axis. So for low frequencies we have a positive imaginary part. So for low frequencies you can realize in principle an inductance with the help of a short circuit stub, or we can say for low frequencies it behaves like an inductance. And then at pi over 2 it undergoes a transition from from positive imaginary part to an negative imaginary part. So in this region roundabout we must think which of the lumped elements has approximately the same behavior. And if you think of a parallel resonance circuit, then the parallel resonance circuit shows almost the same behavior, at least around pi over 2. First, for the frequency, lower frequency, it's inductive, and then it undergoes a transition, and then it becomes capacitive. And now we have here a region where it's purely capacitive. So in this region we can think of realizing a capacitor with a short circuit stub. And now I don't have another color, so perhaps I just take the red color again here. So here we undergo a 0. Also, first we are capacitive with respect to the frequency, and then it becomes inductive again. So this behaves also like a circuit, but now it's a series resonance circuit. So with the help of a short circuit stub, we can in principle realize all these lumped elements, where one must say the longer the wavelength or the longer the transmission line, of course the higher the losses. So it's of advantage only to realize these two elements with a short circuit stub. So the short circuit stub is normally used to realize inductance or a parallel resonance circuit. We speak here of the parallel resonant and here of the series resonant. Now I want to discuss with you the electric behavior of a so-called open circuit stub. Open circuit means that now in our case set L tends to infinity, and if I now again calculate the input impedance of this transmission line, where I let set L tend to infinity, we will get that the input impedance will be equal to set C divided by J tangents beta L, or we can rewrite it like this. This is minus J set C cotangents beta times L, where we have also for beta L the same relations as before. And now I also want to sketch the imaginary part of the input impedance over the angle. So again I assume here to have beta times L, and here we will have the imaginary part of the input impedance set in, and of course also the cotangents function itself is a periodic function, but for beta L equal to 0 it tends to infinity. So we have the first pole here for 0, then we undergo at p over 2 a 0, and then we have the next pole at pi. So this will be the next pole, and of course then we in principle go on periodically. So if I sketch it now, it almost looks like this. We start at negative infinity, then we undergo the transition to 0, and then we become inductive. And again we have here, we come from here, and then we undergo a transition to 0 again. So the behavior of the imaginary part looks almost like this. And now again we can ask which lumped elements can be realized using an open circuit stub. And here you again see that for low frequencies or short lengths, an open circuit stub is able to realize a capacitor. So here for short open circuit stub, a short open circuit stub can be used to realize a capacitor. And here, if we are in the region of pi over 2, then we undergo again a transition from the capacitive value to, to the inductive value. So in this region it again operates like a series resonance circuit, and then we have again a region where we can use it almost as an inductance, and then we again undergo a transition, but now from positive infinity to negative infinity. So in this region it operates, or its behavior can be approximated by a parallel resonance circuit. So again, also with a short circuit, open circuit stub, we in principle can realize all elements, but as I already told you before, since we have to increase the length, and also if you increase the length, of course the losses will increase, so the quality factor will decrease of these elements. And so normally if you use open circuit stub, you will normally use it to realize a capacitor or a series resonance circuit. So these are the preferred elements to be realized with an open circuit stub. Now I want to discuss with you a further special application, and we call this the so-called quarter wave transformer. And this quarter wave transformer, the length is chosen equal to the to a quarter of the wavelength on a transmission line. So you know that we have beta times L, where we have beta, it's 2 times over lambda. And now we choose at a certain frequency the length to be a quarter of the wavelength. So you see here this will cancel, and the result will be pi over 2. But for pi over 2, the tangents function, tangents of beta L, will tend to infinity. And so we can now rewrite the equation for the input impedance like this, that in will be then equal to Zc, and we will have here Zl over Zc plus j, so I just write here infinity, and we will have here 1 over, or 1 plus j load impedance over Zc infinity. So, and if you now in principle approach the length to quarter of the wavelength, then you see you can neglect this against the infinity, and also we can neglect now the 1 against this, and then we can in principle cancel j and also cancel infinity, and we get as a result for the input impedance that in it will be equal to Zc square over the load impedance. So normally we assume the load impedance to be show a complex value, but we can also assume that, for example, the load impedance, if the load impedance is real, then also the input impedance will show real value, because in RF engineering the characteristic impedance is always a real value. So we can also say this goes over into an equation that the input resistance is equal to ZC square over the load resistance. And of course this simple equation can now be used for transforming a certain load impedance into a specified input impedance. So for example, I will do a little example here. Let's assume that we have here the situation, we have here our transmission line, but the length of this transmission line is lambda over 4 at a certain frequency. And I assume that I can choose now the characteristic impedance of our transmission line, and we terminate this with RL, and then we, according to this equation, we also will have at this frequency a real Rin value, and we can now, for example, use this as a transformer. For example, if I choose RL to be 200 ohm, and very often we in the RF engineering we have to transform to an input impedance of 50 ohm, so we choose Rin to be 50 ohm, and then we can resolve this equation to get the necessary characteristic impedance. So ZC will be then the square root of 200 times 50, and it will be ohm, and if you calculate the value, then you will get that the value is equal to this is 10 to the power of 4, and it will be equal to 100 ohm. So what we need to use is a transmission line which has a length, which has a characteristic impedance of 100 ohm, and if we now assume a certain wavelength, for example, we think of an air-filled transmission line, and we think of the frequency to be 3 gigahertz. So then if we have an air-filled transmission line, it's easy to calculate the lambda naught, which will be C naught divided by the frequency, or lambda naught in our case will be 3 × 10⁸ meter per second divided by F. It's F naught, call it, it's 3 × 10⁻⁹ 1/2, so the second will cancel, and we will get this is 0.1 meter. So in an air-filled transmission line, we would have a length on the transmission line which is 0.1 meter or 10 centimeter. So we would have to choose L to be 25 centimeter. This, if I use a length of 25 centimeters of this part of the transmission line, then we will transform a 200 load of 200 ohm into a 50 ohm, and we will have a matching then again in the input of this quarter wave transformer. Sorry, I did a small mistake here. Of course, if I have 0.1 meter which means it's 10 centimeters, so we will have here 2.5 centimeter as the length of our quarter wave transformer.